Well, thank you so much for the opportunity to speak here. I'm Sabetta Matsumoto, and I will be talking to you about knits today. So I am a physicist. My expertise is in geometry and materials. But as I grew up, I did a lot of textiles with my mom's. My mom's a textile artist. And so from when I was a little kid, we were sewing dresses together and knitting together and doing all sorts of activities like this. And as I grew up and started getting into science and math, I started getting really interested in the way that this collective knowledge that that communities have about textiles gets passed down through generation after generation, and it just becomes this folk knowledge. And there's so many people who are just absolute experts at all of this stuff, but we find that it's actually quite difficult to turn that into something that is rigorous and scientific. So that's what my lab has been really interested in. So I'm going to first show you some of the wonderful people in my lab whose work I will be talking about today. So first off, I have Krishma Singhal, who is a PhD student in my group, and she's done all of the experiments and imaging related to looking at the elasticity of knits. We've got Mike Dmitriev, who is a former postdoc who's now at UMass Amherst in the polymer science department. And he worked on the computations related to the same project that Krishma was working on. We've got Lewis Campbell, who is an undergrad from Morehouse, and he's working on a project that's not about knits, but it's about sewing. So we're looking at the ways in which you use the seams that make up clothes to come up with sort of interesting design features, but also try to make them a better fit. And lastly, this is Shashank Markande, who is a former PhD student in my lab, and now he is at UPenn, and he worked on the mathematics, the sort of knot theory of knitting. So there are some other wonderful people in my lab, but these are the ones who I'm going to tell you about today. So our lab has a saying. We like to say knitting is coding. So this comes up in a couple of different ways. So what you see here is a close-up of the dragon shawl. The pattern is called the Dragon of Happiness. It's by Sharon Winsauer. And so what you see on the right here is this is the pattern, the directions that were used to make that. So you see all of these itty bitty tiny little ASCII symbols throughout. Those are code for some manipulation that you do with your yarn and needles. So in some sense, it's a code, you have to decipher it. But we think of it as a code much more the way you think of programming, like a coding language. And this isn't the first time people have thought about this when it comes to textiles. This is an image of the jacquard loom, and this is arguably humanity's first digital technology. So in weaving, so this is weaving, not knitting. In weaving, normally you have pieces of yarn that pass over and under each other. And normally you have these sort of, they're called heddles. You've got these sort of strips that pick up lots of pieces of yarn, and then you thread yarn, you thread like the other yarn through it, and then it changes which ones get lifted up. And that's how you make normal weaves. But the jacquard loom is special. The jacquard loom lets you individually address every basically pixel in your fabric and turn it into like a tapestry. And so basically every time you have a crossing, you can either pick, say, like a 1, which would be this yarn over this one, or a 0, which is this one over this one, for instance. And the way it's coded is using punch cards. And this is exactly the same thing that happened in the early ENIAC era computers. This is how programming worked. You would put your code in, this machine code, into these punch cards, and then you run it through the machine and that executes the program. And so this is, in a sense, the first type of coding that humanity has. Here you can see a more modern version of it, where the tapestry it's making is a picture of a woman's face. So in knitting, we have a language here. Our language is more complicated than ones and zeros. We have all sorts of different manipulations we can do. Each one of these characters represents different things that you do to the yarn over all sorts of different topological manipulations. And in some sense, each of these, I'm going to call them words, these form something like an alphabet or a grammar. And our code is based on that. So they interact with each other in different ways, and they produce different results when it comes to the overall textile. So let's have a look at the knitted stitch. So this is a zoom in on creating a knit. So I have two needles in my hand, one in my left hand and one in my right hand, and each of them has loops of yarn on them. So the process of knitting, basically I take my right needle and I poke it through one of the loops on my left needle, and I wrap the free yarn around it and I pull it through. So knitting is the process of taking loops and pulling them through loops and using this to generate a textile. So if we kind of zoom in at a schematic of what's going on, here's a single knit stitch. And this is what it would look like kind of in a digital fabric. So knits, there's sort of two different basic stitches. I can have a knit, which is when I pull the yarn from the back of the fabric through to the front, and a purl where I pull the loop from the front of the fabric through to the back. And so these are some different textiles I can make using that. So if I just have my fabric that's all knits everywhere, I have this is called stockinette or jersey. This is the most common type of knitted fabric. You'll sort of recognize it as the standard, the sweater knit, it's t-shirts, socks, pretty much everything you own that's knitted is going to be made out of this type of fabric. And if I turn it over, this is the back side of it typically. This is the side where all of the purls are. So it's really, knits and purls are the same thing. It's just one's been rotated by 180 degrees from the other. And so this is the most common fabric that you have, but there's all sorts of other fabrics that we use. So these are just some really common fabrics that are made out of knits and purls. So this one is called garter. It is a fabric where you alternate having you have rows of knits and purls. And you'll notice that this one has these kind of like ribs almost on it. And it's really stretchy when I pull it in this direction. And it's pretty stretchy when I pull it in this direction too. I should say, in contrast, this one here is actually, it's stretchy, but it's not too stretchy. Like your sort of t-shirt doesn't feel like it gets super baggy over the day as you wear it. The next one is ribbing. This is really, really stretchy in this direction. It's like almost an order of magnitude stretchier than the other ones. This one is really common. This is something that you see often in cuffs and collars, and it takes advantage of this extra elasticity. So it keeps a nice snug fit around, say, your wrist, but there's enough room for your whole hand to pass through. And then the last one is a checkerboard pattern of knits and purls. And this one is called seed stitch. And this is sort of an intermediate amount of stretchiness for all of them. And so this is what Mike Dimitriev and Krishma Singhal have been studying, is how do we understand why all of these fabrics, which are basically all made out of equal numbers of knits and purls, just arranged in different patterns, why they have such different macroscopic behavior. So I'm going to take a little break from talking about this, and I'm going to talk a little bit about symmetries. So if you notice, there's all of these little gray dashed lines on this slide. And these little gray dashed lines are telling me basically this is the minimum information I need to be able to repeat this whole pattern. This is called my unit cell. And we're going to explore what this means using symmetries. So mathematically speaking, symmetries are transformations. They're sort of motions of a pattern that leaves the object looking the same. So I've got a couple of questions for all of you. So here are some flags. This Georgia is Georgia the country, not our very own Georgia, but these are flags from around the world. What kind of symmetries do you see in these flags? Please enter this in the chat. Also, feel free to ask any questions in the chat, and I will do my very best to address them as we continue our chat. What do you think? Okay, so I see, okay, great. I'm getting a lot of responses. So mirror symmetry, Tennessee has 120-degree symmetry. A lot of people are saying sort of top-bottom symmetry. Everyone says all but Tennessee can be folded over. Okay, fantastic. So a lot of these have lines of symmetries. They're these mirror symmetries. Even Tennessee does. So this is what the mirrors look like. So Albania, I have one mirror that I need for it. Georgia here, there are 2 mirrors. Tennessee, it turns out you can make with 3 mirrors. Switzerland is 4, Vietnam is 5, and Macedonia is 8. So this means that I don't need the full flag in order to represent all of this information. All I need is some little subsection of the flag and then the rule. So the rule is every time I see a blue line, I have a mirror symmetry. So this, if you're also going to have to ignore the shape of the flag, since all flags, except I think for Nepal, tend to be rectangular, where these mirror symmetries aren't completely respecting that. What about these? So in this one, you'll have to ignore the stripes, like the shape of the stripes on the Korean flag, and the fact that the United Kingdom isn't square. But what kind of symmetries do you see for this? Oops. Okay, so I'm seeing rotational, point symmetry. Anyone else? Someone says mirrors, someone says 4 and 5. So rotational and point symmetry, I guess, are pretty spot on for this response. So each of these has a rotation which acts at a fixed point. So for these, South Korea, if you sort of ignore the shape of the stripes, has a 180-degree rotation about the center, as does Maryland. NATO has, and the UK have 2 90-degree rotations. The ones that are really fun are the Isle of Man and Hong Kong. So the Isle of Man has 120-degree rotational symmetry. So basically I take this leg and I can rotate it over and I get this leg, and I rotate it over and I get this leg. And that's the same thing that we see with the flower petals in the Hong Kong flag. So these are the, again, minimal bits of information I need to repeat all of these patterns. But what about this one? What's going on here? I don't exactly have, well, please answer in the chat if you see what type of symmetry this is. But I don't really have like a translational symmetry, sorry, a mirror symmetry, because the snake's tongues are both sticking out the same way. I don't really have a rotational symmetry because the snakes are all based on the same part of the ground. But what kind of symmetry do I have going on here? I have a repeating pattern. Yes. So I have one, yeah, there's a copy paste symmetry. I have one snake. All I need to know is one snake. And then I take this snake and I put it here, and I put it here, and I put it here. So how can we describe this using a symmetry operation? So I'm going to show you a video from the software that's called Attractor. I highly recommend you go out and try to find a copy of it. But here is what's going on with this type of symmetry. So this is the smallest bit of information here. This is a lion and not the snake, but what it's going to do is the blue or the red and yellow sides are going to roll up and match each other, and then the blue sides are going to roll up and match each other. So now I've got this torus, and so from the torus I can start unrolling this pattern everywhere, and just having this torus is enough to generate the entire pattern that's in the plane. So coming back to our knits, this looks pretty familiar. So we have this type of repeat. We've got a small piece here and it gets repeated. Every time I say knit, I just copy and paste this down. I stamp this out. And so what we want to do in my lab is try to study some of these objects. And one way we do this is using this mathematical idea called knot theory. So knot theory is basically the study of what happens if I take some sort of loop and I entangle it in some interesting way. And the question is, can I untangle this knot or not? Or if I have two different tangled up loops, is there a way I can tell that they're really the same loop? And I'm allowed to do any manipulations I want, except I can't cut it and pull something apart and like glue it together. And so this is what the mathematical theory of knot, the mathematical concept of knot theory tries to understand. So we'd like to look at this in terms of knot theory. So since I know that this is periodic, I can sort of glue the edges I have together. So I can glue this sort of left and right edge with the double hash together along with the top and bottom edge with a single hash. So what I'm going to do here is glue this together. So first I'm going to extend the left and right sides. Now I'm going to glue the top and bottom to each other by pulling them around behind the rest of them. And then I'm going to glue the left and the right side by going around behind that. And so what I've got here now is a knot. So you can convince yourself that you have these sort of Dumbo ear type things on one side and then on the other side. But if I try to untangle these, I will basically just keep finding I've got some little loop somewhere else that I can't undo. And it turns out that as we saw the lion pattern lived inside a torus, so our pattern is a little bit special. This lives inside the glaze on the surface of a donut. So this is a fancy mathematical space that we call T2, which is the torus cross I. That's just like thickening it a little bit. So all of these knit knots live inside the glaze on the surface of these donuts. So we wanted to know what sorts of things can I put inside these dashed lines. And so this is what Shashank has worked on. So he sent me a text with this picture one day, and he had noticed that a lot of the knots he had studied, in fact, every single one of the knots he had studied had some property that's called being ribbon. Basically, this is a mathematical property that if you take your knot and you dip it in soap water, you have some sort of like film that forms where the edge of the knot is the boundary. There's only one type of intersection you can have. You can only have the full like ribbon of the knot passing through a section of the other. You can't have this sort of X-shaped like crisscross region. And he was wondering, are all knitted stitches ribbon knots, or are all ribbon knots knittable stitches? And so he sent me this as maybe a counterexample to all ribbon knots being knittable stitches. And I guess I was at home, I was going to go out for a run. I was like, you know, I think maybe we can knit this. And so I was like, I sort of texted him back and I was like, I think we can, but I'm not 100% sure. So then I went for my run, and on the run, I was like using like yarn and needles in my brain to like try to manipulate the stitches. And I was like, I think I know how to do this. So I texted him back and I was like, okay, we'll bring some yarn and some needles to group meeting on Monday and we'll figure this out. And it turns out that yes, in fact, this is a knittable stitch. It creates these sort of little dollops on the side here. So there's 6 of these stitches. So these he calls the cow hitch stitch. And it turns out that he was just able to use math and these mathematical properties to create a stitch that no one had ever seen in the textile world. So I think that's one of the most powerful things about this method. So getting back to symmetries for a minute, we talked about some other symmetries at the beginning when we were talking about the flags. So we've got here an object that has only mirrors. So this is another animation from a Tractor software. And so this is how you can create the whole pattern. So here is the minimal necessary unit, and each of the white lines is a mirror. So as you go, you roll the object over every time you see a mirror, and that stamps out the top side, bottom side, top side, bottom side. And that is enough to create the entire 3D pattern. So the other type of symmetry we looked at is rotational symmetry. So here's a point that has 6-fold rotational symmetry. This point has 3-fold rotational symmetry. This point has 2-fold rotational symmetry. So we'd like to see how we can use this smallest unit cell to try to create this full pattern. So here it is in a tractor. So here are these centers of rotation. So the hexagon is the 6-fold, the triangle is the 3-fold, and the diamond is the 2-fold. And so what's happening is that little unit gets folded up and then inflated like a samosa. And now the samosa is going to roll across itself around the entirety of the plane. And this is enough, this little samosa is enough to take all of the information that's necessary and create an entirety of a 2D pattern. So we've talked about all of these symmetries, but what's going on with this dress? If you look at the skirt, everything looks perfect. We've got some mirror symmetries through here. We've got some rotational symmetries, 180-degree rotational symmetries here. This seems perfect, like it makes sense. But then when I zoom in here, what's going on? I've got some things that look pretty normal, like up here, but then I get to this V in the center and I don't really know what's going on. So for the rest of the talk, we're going to be talking about curvature. And in particular, we're going to be talking about how do we use the ideas from sewing to understand curvature in the real world and mathematically. So here's maybe an example. So if anyone here sews, this maybe will seem silly, but if you don't sew, you might imagine that if you want to make a shirt, you just take like 2 shirt-shaped pieces and cut them apart and then like just sew them together. But it turns out that this is the pattern that you would use to make a fancy dress shirt. And you'll notice that almost no lines here are straight. Almost everything's curved. The places you see straight lines are ones that say fold or are maybe like obviously where the hip goes, like where you would tuck it into your pants and you wouldn't really notice the line. Everything else seems to have these really intricate sort of curving shapes. And this is necessary to make things fit perfectly. So what's going on here? Let's break this down into 2 types of things that people do. So imagine I have, instead of all of these curved seams, I want to make a little bit of positive curvature. So what can I do? I can fold my fabric in half and then sort of sew a diagonal line through it. And then when I turn it around and pop it inside out, I have this little cone structure here. And so that's what was going on in that dress we saw at the beginning. And so this is what we call a point of positive curvature. And this is used places like busts and things like that. So we've removed some area from it and now we've gotten a cone. Instead of removing some area, I can sort of add some area in. So this is called a godet. Here I've got the full seam and I basically open it up and I stick in a wedge of material. And this gives me a piece that locally looks kind of like a saddle. So it's curving around her knees this way, and then it's curving away from her body this way. And so this is what we call negative curvature. So now let's have a look at maybe what was going on in that dress. So here's some really symmetric fabric. So it has this lovely honeycomb pattern on it, and I'm gonna cut out 1/6 of it. So I started off with 360 degrees around here, and I've cut out this sort of 60-degree wedge of it. And then when I sew it together, I get this. So I've got this one point that has, instead of a hexagon, it has a pentagon. So I've lost that 60 degrees. And everywhere else, I have these perfect hexagons in this seemingly perfect hexagonal order. But you'll notice that I can't keep this flat anymore. Now it's popped out of the plan and it's made this conical structure. So I can take this wedge and stick it into another hexagon. So I've taken now this 60-degree angle and I'm going to add it to this 360-degree angle around here. So I'm going to end up with 720 degrees. And that is going to make this object here. This is a heptagon, so it has 7 sides. And again, this won't lay flat on the ground. It ends up creating this really ruffly structure. So here is a dress made by Andrea Shuey and Robin Sullinger. Andrea Shuey is a costume designer and Robin Sullinger is a physics professor. They wanted to use this type of idea to make a modular dress that could fit any body. So here they use pentagons, so these 5s at places where they want positive curvature, and then heptagons, these 7s at places where they want negative curvature. So the positive curvature is at the bust, and the negative curvature is around the hips and waist. So I used a similar idea to make a jacket. So instead of, in that case, having things that are flat in the plane try to look like they're curving, I have a curved object where I try to make lines that make them look like they're flat on that object. So when they look like they're flat on this object, so this is just a model of my body, and I try to roll them out, I end up with these crazy wiggly lines down here. And so this is a little close-up of what they would look like. And this is what well, not quite the finished project, but this is the sample, the test piece looks like. So as you can see, all of these lines look like they're perfectly straight on my body, even though they were really curved when they sort of came out of the cutting machine. So what about this? What do you think these two things have in common? We've got this fancy French couture wedding gown and these human intestines. So what do you think's going on here? Increased surface area, curves, lots of curving back on itself. Excellent. Those are fantastic answers. Yeah, so I would say all of those are right on target. So it turns out that this has all of these sort of wiggly ruffles. Both of them have the wiggly ruffles. And it turns out that not only do they have these ruffles, but the physical mechanism by which they have these ruffles is the same. So when I make this dress, well, I didn't make the dress, but when the designer made the dress, they had a stiff piece of boning and stretched out a piece of tulle, so the kind of gauzy meshy stuff, stretched it out as far as it could go, and then sewed it together. And then now there's this sort of mismatch. This line up here wants to be this distance, but the tool is really unhappy. It's stretched out too far and wants to shrink up. So when it relaxes, it ends up making these ruffles with a characteristic wavelength. And that's actually exactly what's going on in intestines. So when you are, when you're a fetus and you're forming, one of the first things that happens is this is called gastrulation. So basically you go from a ball of cells to a torus of cells. And that hole that you've made now is going to be what forms your digestive tract. And then parallel to this tube that you've just made is another tube that's called the neural tube, which is eventually going to form your spine. And there's a membrane between these that's called the mesentery. And what happens is that the gut tube basically grows a lot faster than the neural tube does. And you end up again with this mismatched set of lengths and elasticities. So the tube that forms your intestines grows a lot faster than the mesentery can grow. And what ends up happening is that your intestines ruffle to basically accommodate that mismatch. And so this is why the bundle of intestines in my body looks pretty much the same as those in your body. It's not like someone took some cable and just sort of tried smooshing them into our abdomens. There's a method to the madness, as they say. So here's another example of how to get curvature from curves now. So imagine this is going to be a scarf. There are these puzzle pieces we've cut out, and we can just sort of stamp them back and forth on top of each other. But if I zoom in really close to this seam, I end up with this sort of like wedge type angle. So imagine I have alpha and beta are the angles around this point. So if I add these up, alpha plus beta is going to be 360 degrees. But if I were to make alpha plus beta smaller or bigger, I end up now introducing curvature. So here I've made beta a little bit bigger, so I'm going to introduce some negative curvature to it. And basically I can stretch the point of curvature that we saw in those sort of hexagon fabrics out along the entire seam. So here's an example of bending these by 60 degrees on one side and minus 60 degrees on the other side. So these are basically stretching out all of that bending. And I end up with these two sort of pattern pieces, and we can join them together and make this guy here. And so what Lewis did was he created these pieces and then sewed them together. And so this was basically taking that bit of negative curvature and trying to smooth it out across the entire scarf. And so he came up with two different patterns. So this is the one I just showed you. And then here is another one. So you'll notice that this one has a longer edge on top and a shorter edge on bottom. So that's going to give you this nice curve that kind of fits around your neck. So this fits really gorgeously on this dress form. So negative curvature, it turns out, is something that we don't just create using fabrics, but it's something that you do see in nature. So this is an example of a nudibranch, a sea slug swimming, and it's got negative curvature on its mantle, and it's using that as a way to swim. Here we have some coral and some curly kale. And what's going on here is that both of these are maximizing their area, because area for them is how they produce food, whether it's the coral polyps getting to catch more yummy things coming through the current, or it's the kale catching some sunlight. And then lastly, this is a calla lily, and this I honestly don't know why this one's curved. It's my favorite flower, so I thought I'd put it in. So negative curvature is something that is really fascinating to math as well. So this is a really famous piece by M.C. Escher. This is something that was inspired by a conversation with the mathematician Donald Coxeter. And this is called Angels and Demons. Basically, at the center, you've got 3 angels, and their wings are interlocked with 3 demons. And then as you go out a little further, you see, okay, well, here's another place where I have 3 angels interlocking with 3 demons. And you can kind of see this motif repeating over and over again. But why isn't this tiling the plane? Why are they all getting so much smaller as they go out? So let's have a little bit of a look at what's going on. So these center angels and demons, if I take all of their wingtips, I can inscribe a circle around them. And then if I go out to this set of angels and demons, I can inscribe a circle around all of their wingtips, and go out to these guys, and so on and so forth. So I can inscribe circles around all of these wingtips. And now let's sort of look at what's going on. So I'm going to fade out the lithograph and just sort of show you what these circles leave behind. So each of these circles looks kind of like a hexagon, and they're all kind of hexagons. These look kind of like irregular hexagons, but you'll notice that there's 4 hexagons that meet around every point. And what hyperbolic space, which is what mathematically we call a space that has negative curvature everywhere, basically is doing is you want to imagine that each of these circles is the same size. This is just kind of a map projection that kind of smushes everything out. But you want to imagine that each of these is the same size. And you'll note that hexagons, we get a nice honeycomb pattern if there are 3, but if there are 4, you've got a whole 120 degrees of extra angle everywhere. So this is basically what that would look like. This is hexagons that meet around every corner. They have 4 hexagons that meet around every corner. And this is something I turned into a blanket that is here. And here's a pattern for that blanket. So you can either use the QR code or go to my website is matsumoto.gotech.edu/math3dprint/ braces 6,4 close braces.pdf. I couldn't resist trying to make this out of knitting. It turns out, sadly, this won't scan, but I thought it was kind of a cute thing anyway. And if you're interested, you can find me on Twitter. I'm at Sabetta_, and I design a lot of mathematical jewelry. So some of that I'm wearing now, I guess I should hold up. And you can find that at my Shapeways site, Sabetta's Mathematical Creations. Sorry, this is a little bit longer than I think you had anticipated, but you've been a fantastic audience, and I would be very happy to take any questions that you have.